Hello, everyone. My name is Eleonora E.Isotta, and I'm currently a Marie Curie Fellow at the Max Planck Institute for Sustainable Materials. And today I would like to talk about our recent article on local thermoconductivity patterning in rotating lattice single crystals of anisotropic antimony sulfide. And you can find the link to this article at this QR code. And this article was developed and written while I was a postdoc at Northwestern University. I should say this presentation was also given a few days ago at the Frontiers of Thermal Transport in Materials Spotlight series promoted by MRS. Okay, let's start with the introduction. So we know that controlling the way materials conduct heat is very important for several applications. When we think about thermoelectric devices, we typically try to select materials with very low thermal conductivity because this allows to convert the majority of the heat in driving the heat carriers as opposed to lattice vibrations. On the other hand, when we think about micro and high power electronics applications, we typically have a problem of having to dissipate large amounts of heat in very narrow spaces. So typically one selects for high thermoconductivity materials and high conductance interfaces. When we think about advanced thermal management applications, more exotic properties of materials are becoming interesting. For example, materials with very high thermal anisotropy, or materials that allow for a dynamic control of the conduction properties, for example, in thermal switches. And when we think about heat transport in materials, one feature that is really important in controlling the properties is microstructure. There's a lot of type of microstructures, but in general, introducing a larger density of microstructural defects impacts thermal transport. For example, when we introduced a high density of grain boundaries because we reduce the grain size of a polycrystalline material, we typically expect the thermal conductivity to be suppressed. The same thing happens when we introduce precipitates and we increase the density of these precipitates. Another case is when we introduce dislocations because they can also act as a scattering center, and we can notice a suppression in the thermal conductivity with increasing amount of dislocations. So on the one hand, we have seen that microstructure strongly impacts transport. On the other hand, we see that we can have very different types or very different flavors for microstructure. And here I want to briefly mention a work that we recently published where we delved into the topic of grain boundaries, and we show that grain boundaries can really exist in very different types. For example, we know that we can have low angle boundaries or high angle boundaries, where with angle I mean the misorientation angle, and they can promote different level of segregation at the interface. But on the other hand, we can have different structural units and different atomic arrangements that form at the boundary. So again, microstructure strongly impacts transport, but for the same microstructure type, we can have different flavors. And so a natural question that we had was how do specific microstructure flavors impact thermal transport? And to try and answer this question, we have been working recently with microscale thermal conductivity imaging as a method to really see the properties of individual microstructure types. And we have been doing this through frequency domain thermoreflectance, or FTTR. And analogous thermoreflectance techniques have been used to image the thermal transport properties of materials from, let's say, other groups in the thermal transport communities. And just to give you some examples, this work analyzed the thermal boundary conductance due to different adhesion layers present on the surface between a transducer and the sample. This other work instead noticed that regions with a high density of grain boundaries in diamond were showing a highly suppressed thermal conductivity. And this other work was investigating the bonding quality between two different films by using the depth sensitivity of FTTR. And specifically, we were interested in the question of microstructure and the behavior of different microstructure types. And we have done quite some work recently on grain boundaries, where I guess the main key takeaway is that when we measure individual grain boundaries, these are thermoconductivity images collected around single grain boundaries, we typically observe a local suppression in thermoconductivity that spans a few microns around the boundary. And we have analyzed the data through what we call the Gibbsian excess method, where we try to get an estimate or a proxy for the thermal resistance by using an excess approach. So if we plot the thermal resistivity, we typically observe that the thermal resistivity locally increases at the boundary, and we take our excess boundary resistance as the integral of the local resistivity minus the grain resistivity. So basically anything that is in excess from the grain is lumped together and attributed to the boundary. And this is the estimate of resistance that we calculate for our boundaries. And we have employed this on different material systems, tin telluride and silicon. And briefly, the main conclusions are that we do notice a local thermoconductivity suppression in the grain boundary region, typically spanning a few microns of width. And at the same time, we see that this thermal resistance estimate that we obtain depends on the misorientation angle. This is something that we saw in tin telluride, where high angle boundaries tended to show a larger thermal resistance compared to low angle. And in silicon, we specifically studied boundaries with the same misorientation angle to try and see what other features are important. And we saw that the interface morphology seems to be definitely an important feature. Okay, but today I would like to talk about another case of microstructure that we have studied recently, and this is antimony sulfide rotating crystals. So antimony sulfide crystallizes in the orthorhombic PNMA crystal structure that is characterized by these layers, corrugated layers of atoms. And what is a rotating crystal? So the easiest thing is for me to show you how it is made. So the samples were actually made by the Janes group at Lehigh University, and they took antimony sulfide powder and brought it above the melting point and then quenched it to retain amorphous or glassy antimony sulfide. And then they employed a laser that was dragged on the surface of the amorphous material to locally crystallize, creating crystal lines of antimony sulfide that you can see, for example, in this image. And when we do an electron backscatter diffraction analysis over some of these lines, we can see that the background is black, and this is where the EBST does not index any crystal structure. So the black background is the amorphous region, and where the laser was passing, we see some color. So seeing a color in EBST means that we have crystallinity there. Although we do not see a uniform color, meaning that the orientation is not unique, but we see a local change in orientation. So what is happening here? So let's follow just one of these lines to better understand. So at the beginning of this line, the crystal is oriented such as to have the B-axis pointing out of the screen. But then if we look just next to it, the crystal is rotated a little bit, and it keeps rotating until at this point it has the C-axis that is pointing perpendicular to the screen. And the rotation continues until it basically forms two full rotation about the A-axis along the line distance. But this is not the only way that rotating crystals can form. For example, if we just look at the line below, we see that the crystal here starts by having the A-axis that points out of the screen, and then the rotation this time happens faster because we have 4 full rotations along the same length of the line, and it happens about the b-axis. Okay, and so, of course, we were interested immediately on how do these amorphous crystal regions affect the thermal conductivity, and does this rotation of the lattice affects the thermal conductivity at all? And so to respond to this question, we performed thermal conductivity imaging in some of the areas that we had measured with eBSD. So let's start from the first one here. So this was a polycrystalline dot that was generated by stationing the laser in one spot. And what we can see is that the regions around the spot that are amorphous are associated with pretty uniform and low thermal conductivity, whereas the spot is associated with a higher thermal conductivity and with larger variations. Although we don't really distinguish the effect of specific grain orientations because the grain size is very small. And when we measure in regions with crystal lines, the behavior is somewhat similar. So we see that the amorphous areas in between the lines show a more uniform and low thermal conductivity, whereas along the lines we see a higher thermal conductivity, but we see also larger fluctuations in the thermal conductivity. And these do not seem to be random because they seem to be actually relating to the crystal orientation. In particular, we see that regions oriented along the a-axis show the largest conductivity. Regions oriented along the b-axis show intermediate thermal conductivity values, whereas regions aligned along the c-axis show values that are really barely distinguishable from the amorphous regions. And so a person that is familiar with thermal reflectance method knows that the sensitivity to the different thermal properties can vary with the modulation frequency of the lasers. So long story short, what thermal property are we actually sensitive to when we do this measurement? So we have run some sensitivity simulations, and in the frequency range that we have chosen for our measurement, that is the one in between the dashed lines, we are mostly sensitive to the cross-plane thermal conductivity and the thermal boundary conductance between the transducer layer and the sample, whereas we're not really sensitive to the in-plane component of the thermal conductivity. So what this means is that when we see these thermal conductivity images, we're really measuring the thermal conductivity direction that coincides with the eBSD normal direction, so the direction perpendicular to the screen. And so we can just summarize the data that we obtained. So first of all, we saw that amorphous area tends to show a low thermal conductivity on the order of 0.6 watt per meter Kelvin, quite in line with thermal conductivity predictions from the glass or diffusion limit. Whereas when we sample regions oriented along specific crystal axes, we see that regions oriented along the c-axis tend to have a thermal conductivity that is very similar to amorphous regions, whereas along the b and the a-axis, we respectively see a roughly 2 times and roughly 4 times larger thermal conductivity. And we collaborated with Berkeley Lab to perform some first principle calculations and predictions of the thermal conductivity. And the values they obtained were quite aligned, both in terms of values and in terms of anisotropy ratio to what we measured experimentally. So having their simulations really allowed us to try and delve a little bit deeper on what are the origins of this thermal conductivity anisotropy in the system. And what they actually realized is that if we see the average group velocity along the different crystal axes, we see that the trend mimics the trend that we see in thermal conductivity, as the a-axis tend to have a larger group velocity than the b and then the c-axis, which is the same as what we see in the thermal conductivity. Another interesting aspect that they noticed by looking at the different contribution, both in terms of type of, let's say, carrier and in terms of frequency to the thermal conductivity, is that along the B and the C axis, most of the phonon contribution comes from low frequency phonons, because at high frequency, basically the phonon contribution plateaus. Whereas when we look along the A-axis, the phonon contribution still rises at high frequency, meaning that the optical phonons are important for the thermal conductivity along the A-axis, unlike the other two crystal directions. And but still, the question remains open: what promotes the thermal conductivity anisotropy that we see in the system? And I should say, we have a layered crystal structure, as you can see. So we were not extremely surprised about having a low thermal conductivity along the C-axis, because this is the direction that goes against the layer. And we typically have lower thermal conductivity in layered material in the cross-layer direction. What at least I was more surprised about was the large discrepancy in the thermal conductivity along the B and the A axis. And so we have performed some electron localization function analysis, and we have actually noticed that the antimony has an expressed lone pair. So the fact that the lone pair is expressed means that it occupies a specific position in space, which is something that we notice because if we draw the octahedral bonds of antimony, we see that the lone pair is sort of stretching and pushing the bonds and forcing basically the structure to take on this corrugated layer, so the corrugation of the layer. And interestingly, the lone pair is expressed and causes the corrugation along the B-axis. But when we look along the A-axis, we see that the lone pair does not cause any visible distortion of the bond along this direction. And we have calculated the bond strength from the interatomic force constants. And what we notice is that we have softer bonds and lower bond strength along the B-axis compared to the A-axis. And so the conclusion is that lone pair seems to soften the bonds and drive this corrugation, but this happens primarily along the B-axis and much less along the A-axis. And just to show you some comparison, if we look at antimony telluride, which is a close analog of antimony sulfide, because it's still a chalcogenide, in this case, the antimony lone pair is not expressed. And as a result, the crystal structure of antimony telluride is not orthorhombic, but is rhombohedral. And the properties are transversely isotropic, meaning that the A and the B axis show the same thermal conductivity. So again, we think that the lone pair expression is responsible for the softening that we see along the C axis because it basically opens the gap between the layers, but is also responsible for the corrugation and the consequent softening that we see along the B axis. So in conclusion, we have seen that thermal conductivity can be employed to detect the strong thermal conductivity anisotropy in antimony sulfide. And we have seen that this anisotropy seems to stem from the expression of antimony lone pairs. And finally, the part that I feel is interesting as an outlook for the future is that this is let's say, patterning the structure of a material by using lasers is a very attractive and versatile technique for patterning the thermal properties. In fact, people at Lehigh have really delved into this problem, and they were able to demonstrate that with laser, they could, of course, create any shape, but also they were really able to control the orientation of the crystals that form by changing parameters such as the laser power or the laser scanning speed or the orientation of the initial seed. So being able to really pattern a line however one wants and controlling very precisely the crystal orientation in an anisotropic system basically is a way to allow thermal property control at the microscale. And with this, I would like to thank all the people that participated in this work, in particular, the group at Northwestern University, but also collaborators throughout Lehigh, Berkeley Lab, and LIST. And I would like to thank my funding source through the Marie Curie Fellowship. And thank you very much for your attention. If you would like to find additional details about this work, here is a QR code that links to the article. And feel free to reach out with any questions or comment that is really appreciated. And thank you very much.